Okay, so let me start. Just a few words about myself first. So I'm also an organizer. I got the honor to do that by the team. So I'm now associate professor in economics here at the University of Lausanne. My PhD originally was like in nuclear astrophysics with focus on supernova simulation, but the last 13 years I work in econ and finance. And I exist also in social media. And if you are interested, so I also have relatively a lot of codes to solve models of deep learning or also other methods. There are comprehensive generic methods to solve recursive equilibria. So if you're interested in some of that, you can find that online. So that's me, your physical host here in Lausanne, just that you know to whom you're talking to. Okay, so this introduction will be essentially, I will talk about the fundamental building blocks of deep learning. So that means I will talk about the multi-layer perceptron, feed-forward networks, how you train the neural network. So, all of you had econometrics classes. So like how you determine the parameters of the model you have at hand. This is what you want to do. And then, we introduce some basic terminology that is used in machine learning in general and in deep learning in particular. Then there will be there are three Jupyter notebooks that I will share with you. And conditional on the time, we will quickly step through them, or you have to do that on your own. So I will just hand to you a gradient descent example where you see how you can actually fit the function to data or artificial data. And then I will provide you with two notebooks that show, because you don't need to implement neural nets, luckily yourself, there's a lot of highly tuned good libraries out there. And one of them is Tensorflow, the product of Google. But luckily, as I will mention, the Tensorflow was very cumbersome to use for a very long time. And then they started to build API, so an application interface to TensorFlow, which is called Keras. But now they recently also announced that this interface is also usable in the context of JAX and PyTorch. So this is our other main libraries used in deep learning. So essentially, if you use this API, you can use different engines underneath without having the need to rewriting the code. So we'll see that in a moment. But first, few words on the context, like with the rate, I call it the rise of neural networks. We have all seen this enormous impact of neural nets. I mean, of course, like you have all heard about neural nets beating humans in video games, but that's already like almost a decade ago. But more recently, it's interesting. Like if you follow the literature, if you go to drug design, neural nets are used, so you don't need to go to the wet lab anymore and do all sorts of experiments with molecules. You can use deep learning to accelerate this process massively. Self-driving cars, you name it. For those of us, who need to write a lot of papers and text, what is more interesting is of course, ChatGPT that can generate you. It's generative AI, they call it. So like you can ask questions, it responds to you. You can use, diffusion models. So like here I asked it, draw a bird teaching himself deep learning in the style of Kandinsky. And then you get such pictures. You can ask ChatGPT to help you with coding. So it's an enormous transformative character. Self-driving cars is another location, where we exposed to deep learning. Old bad movies can be colored. That's another application. So I put here some videos, like if you go to warehouses of Amazon or other places, you have now robots that carry around stuff. Replacing is a bad word, but helping humans to do heavy lifting and stuff. Quite amazing. So I put in here a few videos. So and of course, like your cell phones, right? This full of hardware that does AI / deep learning and help you. Just think of pictures that are, if you tag them once, you can search in Google Photo for your grandmother, and it will find a remote picture or all the remote pictures where they are detectable. So we're surrounded by that. But deep learning is not new at all. So the building blocks, if you look into the history, Pitts and McCulloch, they started with a model of neurons already in 1943. So this is 80 years ago. It's quite amazing. And so there's all sorts of developments. But now the question is, of course, like, why would it take so long, until they essentially emerged? So why now? And I can give you more complex answers, but like the short answer is essentially, so there's three components. It's commonly believed at these days that make them so persuasive in our daily life. One is, so neural nets or deep neural nets, they're extremely data hungry. So like for empirical applications, you need a lot of data. We live in the age of big data. So like we have, I believe, I checked it up yesterday, 5 or 6 billion inhabitants of this planet, they use the internet. Whatever you do, there's a trace, so there's an enormous amount of data all of us jointly generate. Be it your stuff in Amazon, you go to social media, whatever. So there's an enormous amount of data produced there. Then there's of course science experiments. If you go like to Geneva, the Large Hadron Collider, where they do these particle measurements, it produces petabytes and petabytes of data per second. Like it's an enormous amount of data there. And then even, and now this brings me to the second point, the hardware, the compute power, an ordinary graphics processing unit, or a GPU called in simple words, or tensor processing unit. So like we have experts over here who work with those devices a lot. They're simplified computers, like they have simplified hardware than what you would have on a laptop. But it's very good at few operations, particularly linear algebra, dense linear algebra. Operations you have to train neural nets, they perfectly fit to this sort of hardware. So a GPU these days, they reach teraflops of performance. So that means 10 to the 12, say, loosely speaking, additions of subtractions per second. And these devices, they're not that big anymore. You don't need to fill a room of hardware. You have it essentially as a paper of Jesus was, you can fit it under the desk. So like, it became sort of democratic access to hardware. And then the last point is indeed, one of my papers I worked on the longest was a paper on sparse grids. This took me, I had to write it in C++ and Fortran. It took me years to get it up to speed. Now essentially half of the planet, working in the private sector, they help to improve packages like PyTorch or TensorFlow. So like, you can just, the community is very nice in a sense. Like they share their software. It's open source. It's not closed source. So like, the combination of having access to data, having access, relatively simply to very sophisticated hardware for relatively cheap money, and having the ability to have access to tuned software. So this allows us, not only us in the economics and finance, but also in the other fields, to actually focus on the core components, the research question at hand. So that's kind of reasons why neural nets are very emerging. Now there is, of course, going along the line of being very friendly community. There's also like a lot of good teaching material out there. So like if you really want to have like deeper view into some subtopics, there's for instance a relatively new book by Bengo and Goodfellow. You can download it for free to PDF. It's a bit of an older book by Bishop, pattern recognition, machine learning, but it still like gives the very basics quite nicely. Also, like so to do this at I believe at Microsoft, so they made it also publicly available. And then if you don't feel comfortable with some of the mathematics, so you will see most of the mathematics in deep learning is quite simple. It's undergrad mathematics. But if you want to have more refresher on what you need, there's also a book that I like. It's relatively recently, and you can download it for free, Mathematics for machine learning. Now, before we go into deep learning, let me just put some terminology straight. Because sometimes I get a bit nervous. It's probably just me. Everyone these days, they talk interchangeably of AI, neural nets, blah blah blah. I don't like that too much, but it is as it is. Probably it's due to the media. But so this is from a book from Scholle, godfather of this Keras API. So I like this plot quite a bit because it puts things into perspective. So you could envision there's a field which is called artificial intelligence, and they write there definition of the effort to automate intellectual tasks normally performed by humans. So this is artificial intelligence per se. Then a subfield of artificial intelligence would be machine learning. And what is machine learning in short? So for that, we first need to go to a simple diagram in the context of supervised machine learning. We'll get to that in a moment. But like classical programming would consist essentially, you have data, you have rules, and you have a program, and this gives you answers. So let me be explicit. Say you have a partial differential equation. You write that you discretize your problem, then you choose your multi-grid algorithm, you press play, it does something, and then it spits out the answers. In machine learning, it's a bit different. In machine learning, it's a bit different. For instance, in the supervised setting, so regression case, so you would have data and answers, so labeled, and you would find rules. It's a way to look at machine learning. And one particular technique within machine learning, that would be deep learning. So as you will see, it's a very powerful function approximator in the end of the day. But like just so you have AI, machine learning, deep learning in the bigger scheme of things. Now there are a variety of types of machine learning, some of which you may know from your basic econometrics courses, and some not. So like the basic and probably most often used subtype of machine learning is supervised learning. So that means you have labels, and we get into a moment. So essentially you have an X and a Y, with a cloud of points, you can fit in a line. That would be the example. Now there's two subtypes of supervised machine learning. That would be classification and regression. So like if you want to predict integer values, say you classify the type 1, type 2, type 3, type 4, or like sick, healthy, that's classification. Regression, as the name says, is a prediction of a continuous variable. It's probably, I know for sure you all know this. Unsupervised machine learning is a bit different. So there you essentially just have observations and no labels. Say you have like a cloud of points, and you would understand what could be the underlying distribution or like data generated process. That would be unsupervised learning. And then the third class, which is probably most interesting for us to some extent, is reinforcement learning, where we want to find optimal policies. So you could imagine a robot that wants to find the optimal decisions within an environment subject to some rewards. Now let me just quickly go through all of the types with a brief example. So supervised machine learning regression would be just a simple line. Okay, so you have like these red data points. Then you gaze at the points and say, okay, let me fit in a line. So what is a line? It has two coefficients. say W and W naught, so the offset and the slope. You have the data. Okay, what do you need to do? So you write down a model, say a linear model. You have some parameters and you need to determine them. We'll get to that later, but this is supervised machine learning, prediction of a continuous value. Classification would be, for instance, say, here we would have, customers of a bank, and they would look at at every customer along two dimensions, say income and savings. And then they would have like historical data on all the customers, and then they could say, okay, there is some customers, they have a high income but low savings. So like typically in this field here they default, and up here they don't default. So like you would fit a model. Then if a new customers come, they would know where to put you. And then conditional on that, you would get a loan or not. So that would be supervised classification. Now, unsupervised machine learning, as I said, you don't have labels. Before we had labels, so we had X and Y. Unsupervised, you could look, for instance, at cartoons. Now, say we have here a bunch of ducks. You have here Mickey Mouse. You have here a rabbit. You have another duck. Now you let unsupervised machine learning algorithm run. So Bayesian mixture model would be one. So you want to detect the underlying structure of the data at hand. What could happen is, depending on how you fit that thing, it would split into two groups. But now, it would choose ducks and non-ducks. It could have chosen different way to splitting the data. They could have chosen Disney and no Disney characters, right? So this is already, as soon as you have label, things become a bit tricky. But you get the basic notion. You have regressions. You have labels. Unsupervised machine learning. You may want to to come back to real data sets. So you have like a cloud of points, and you may want to understand. Say here you would have like 3 normals that generate this sort of data. You would want to figure out what are their mean and covariance matrices. Reinforcement learning, the last thing, this would deserve an entire week of lectures on its own. Loosely speaking, you all know dynamic programming, and we will hear later today from Tensorflow about dynamic programming. So like reinforcement learning and then dynamic programming, is sort of the same logic, right? So you want to find optimal policies of agents within an environment. Now, before I get to neural nets, let me just again say one more word, how do you build an actual machine learning algorithm, right? Say here in the context of the regression settings, so we have supervised machine learning regressions. Let's say we have here living space of a flat. We have the rental price, and then we have this cloud. And now we would want to say, if I wanted to rent a house with 4,000 square meters, what would be a fair price to rent that place? So how would you proceed? And this is, again, I'm going here very fast. I just want to bombard you with the fundamental terminology, or remind you of the fundamental terminology. X, they are called the input variables, or input features. Y, so that would be the y-axis. They're called output or target variables. So that these are the variables that we want to predict. A pair of those, so X and Y, they're called training sample. And the entire set of those, they're called a training set. And then H, that would be your model hypothesis. Can be anything. In a simple case here, it would be just a linear regression. So we have 2 parameters. But if you replace H by a neural net, it still holds. So the age you can pick, it's your model. And of course, a line is not very expressive. A neural net, as you will see, it can have thousands, or actually the big, in the big language, natural language processing models like ChatGPT, they have like billions of parameters, right? So this model age just becomes much richer, loosely speaking. But then mechanically, you need to choose a model. Once you have the data, you choose a model. To determine the optimal parameters, you need to define the cost function. Here that would be the mean square error. There are other cost functions. And then you need to somehow minimize this expression. This is all what machine learning is. So in three, well, 2 bullet points, but like you choose a model, you define a cost function, you have an algorithm to determine the optimal parameters. That's all we will do the rest of the week. The art actually is, say the rest of the week, most likely we talk just about H being a neural net. Here the tricky thing is to choose that wisely such that it reflects your economic problems. I think this is the hard part. The optimization procedure is some sort of easy and hard at the same time, because we will need to rely on highly tuned software, but we can help the software again by choosing our neural network architectures such that you can find this optima quite quickly. Now, computationally, we need essentially, few building blocks. Of course, the data, actually generated with the computer itself. We will need linear algebra packages, as you will see, statistic tools, and optimization routines. So this sort of, the ingredients you need to put into your magic cauldron to do machine learning. So this is sort of the basic terminology. And now let's jump from that channel. By the way, I'm going very fast, I understand, because I had to do this introduction. Is there a question so far? And please feel free to interrupt me for clarifying questions anytime. Okay, then with this general overview of machine learning, let's now go into the details, or like the introductory details of artificial neural networks. So as I mentioned, they're out there, basic ideas since the 40s, right? So people try to mathematically model how a brain works. So I'm not a biologist, I'm not a neurologist. I don't want to talk about this. For me, a neural net is just a very powerful function approximator that is inspired by considerations in nature. So let me just start. So what is the fundamental building block of a neural net or a deep neural network? It's a single neuron, and in deep learning language, the single neuron is called a perceptron. So what is a perceptron? So let me go here a bit. So this thing works as follows. So you have here multiple inputs, x1 to xm. Just forget about the one for the time being. They could be, in economics terms, they could be your state variables. Okay? You take those input states, you weight them with some weights W1, W2, W3. That would be that part. So, this is essentially just a linear model for the time being. Then you have input 1. That's called a bias term. So it allows you to shift essentially from the left to the right. That would be you multiply 1 with this W0. So you have inputs, you have weights, you add them up to a single value. And again, like the inspiration is from nature, you have a neuron in your brain, and if the signal strength is above a threshold, it fires or it doesn't fire. Then once you have this sum, you have the nonlinearity. neural network language that's called an activation function. It's very important. Otherwise, we would not be able to fit nonlinear models to data. And then you have your output. So essentially, you could imagine, so you would have this observation y, you have the input x, and you have in between, you have some coefficients to be determined. And now let me just make a quick link. If you go to matrix or vector notation, now one of the reasons why, I mean, there are many more, but like one of the reasons why now GPUs come in handy when you need to work with this sort of well, function approximators is here. So like we can, so at the moment this weight is a, you know, is a vector. Later on it will be a matrix, or, you know, tensor. That's where the word TensorFlow comes from. This is just a, say, a matrix or a vector. Now if you rewrite that, you see here there's a dot product. Or later on it will be matrix vector multiplications. GPUs or TPUs, like this special purpose hardware, they're good at that. They're very good at that. So you can have like a high arithmetic intensity and neural nets. You know, later on, you know, if you have here like 1 billion entries, you have like a big vector. So like your objects of interest here, this number of state variables could be dozens, hundreds, whatever. So I mean, in Econ probably not, but like if you go to what people do in the industry, like, you know, pixels, big color levels, etc. If the input dimension can be thousands of dimensions, right? So billions of entries, thousands of dimensions. You know, you can benefit from something that can, you know, do vector well, those products well. And now I haven't talked about the nonlinear activation function at this point in time. Let me actually go a few steps forward and then I get back again. So far, you know, if we would not have this nonlinearity, you know, no matter how many weights we would have, and so here we have a data set, red and green dots. So you could clearly, you know, by hand separate into two classes. But with a linear function approximator, there is no way to separate the two. And intuitively, this nonlinear activation function will allow you to do the separation of the two classes in that case. So that's important. So that's the motivation. Let me go back. Now, you know, historically, when people work with shallow neural nets, we will get to that. So you have like, you know, say input, output, and something in between. People often work with so-called sigmoid activation functions that have a bunch of nice properties. You can also use them still in the classification context. You could imagine, you know, like if you have two classes and you map the output between 0 and 1, you can assign probabilities, you know, being from one or the other class. So this is sort of one famous activation function. More recently, I mean, here are just the classicals, and, you know, people invent constantly new activation functions. There's like sigmoid. The tangency hyperbolicus is an activation function that maps between -1 and 1 in a nonlinear fashion. So one of the industry standards these days is ReLU, so rectified linear unit. Very simple, so it's 0 or like, you know, x equal y. There's, you know, again, at the moment, my favorite ones are CeLU or Swish. I get to that later. For making computation, you know, sensible. The activation functions, they should have a bunch of good properties. You know, like analytical gradients is one thing. They shouldn't have too many parameters, you know, to make it computationally efficient. But more to that later. But the key is to remember you need this nonlinearity to be able to deal with nonlinear data, predict nonlinearity. Before we go to the neural net, let me just once more go to this perceptron. Now let's assume we were to know the weights. Just say we have a two-dimensional input, we have this bias, and say we have like 3 weights given. So we have 1, 3, minus 2. That's sigmoid activation function. So how would you, evaluate that one? So you would have like 1 plus 3x plus a minus 2x2. And then you would plug that into the nonlinearity. And in the simple case, this is of course just a two-dimensional line. And now, if you think of classification, just for the time being, this also has, of course, a directional component. So that means essentially, if you're on one height of this line, it could be of class 1, and if you're below, you're of the second class, so healthy and sick. So just, to keep the interpretation. So we have seen that one, but that's the perceptron, that's the signal building block of a deep neural network. Now this is boring. Now let's not very rich to do fancy stuff. Now let's move on and think of first of all having multiple outputs. Say we want to do time iteration or policy iteration, so we want to approximate multiple policies at the same time, subject to a high-dimensional input. So how can we do that still in the context of perceptrons? So let's just add, instead of having just one of those, having 2 of those. The difference to what we have seen before is essentially, before the weights they were in a vector, but now we have weights for x1, x2, x, all the x's going to x1, all the x's pointing to x2. So this thing now is a matrix. So we can have the simple setup, multiple outputs. And from that, we now build a trivial neural net. How do we do that? We have still the inputs. Here we have the outputs. That's what we see. That's what we either if you have empirical data, you have X, you have Y. And now we add something which is called a hidden layer. So now it starts to become, more interesting. We don't observe the output on those. We just observe Y and X. And that's, again, all you need to know for simple deep learning, right? So you have here weights. Now you have here also second weight matrix. What you do is, you have here again, like if you go to Y4, for instance, you add up all of them, get the weight, you apply the nonlinearity, but you do this for all the neurons. To go to the output, you have again here all these weights, combine them, and you add subject on what you do on the output layer, you add the nonlinearity or not. So that's all. So you see, this just will turn out to be a gigantic sum. Just a very big sum, and this again brings us back why hardware is important for neural nets. You just need to evaluate somehow this gigantic sum to make a prediction.
So yes. So yes, is there a superscript for G function for the first arrow and then the second?
So okay, this is a bit sloppy. So in principle, you have here, it depends, but like usually in this plain vanilla neural nets, you would have here everywhere the same activation functions. But you're of course right, you could have here, say ReLU, and here you could have sigmoid. So you're right. This is a bit sloppy, my apologies. Good attention. Yes. Then just
question in the back.
Yes.
Obviously, like the advantage in practice of having it in a layer as opposed to just going directly from the input to the final output.
So like okay, do you need this hidden layer? So like there's a lot of math involved, and there's a universal function approximator theorem that, and this is pretty useless for now, but it tells you if you have one hidden layer with sigmoid activation function, I believe, you can prove that you can approximate, if in context of regression, you can approximate pretty much any reasonable function. And also like for classification, you can classify pretty much everything, but you need this hidden layer, and I can send you the math, but you need that, otherwise you can't. More recent mathematics, and the problem with this proofs, it's by Siebenko and Horning-case, they don't tell you, and this is one of the key issues of neural nets in general, they don't tell you how to choose this architecture. So they just show you the limit, of an infinite amount of hidden neurons. You can approximate everything, but this is not, of course, what you want, because all of us are here because neural nets, they can alleviate the curse of dimensionality, right? So most of you probably learned in undergrad or in grad, if you want to do value function iteration, you write down a grid, you add two state variables, you wait an infinite amount of time, you're unhappy, and this is what you want to move away from. You want to have like a rich model with 100 dimensions, still run it on a laptop, in half an hour you have a solution and you move on from life. So the thing is, well, this is kind of an extensive answer. You need that to have like this universal approximative property. But more recent mathematics has shown, for instance, they get pointed to literature. If you add a bunch of hidden layers and you have a particular type of network architecture, you can bound the rate of convergence of neural net from above by sparse grids. So like they will converge faster than sparse grids. I mean, of course, on strong assumptions, but does that answer? Okay, now, so just for notation, so often if you go to some textbook or whatever, sometimes if you have like, it's called fully connected neural net, so if you have like all-to-all connections, often the literature you just do here across. But this is just like, this is called a shallow neural net. Input, hidden layer, output, shallow. This is not where the power comes from. Lately, where the big progress was in, is you add a lot of layers which are not too wide. This is then a deep neural net. So you don't have one hidden layer, but you have a lot of hidden layers, probably not even too many neurons. Conditional on the applications, this architecture, to come back to the question we had before with activation functions, you can have a very complex architecture with the choice, of how many neurons, what are the activation functions, etc. This is called architecture. And the simple most, like where you have like all-to-all, they're called like a fully connected deep neural net. So deep for many hidden layers and fully connected, because you have everywhere the full matrices. But the principle is the same. You have a lot of these neurons, you have point-wise these activation functions, and then you go on. So I covered that already with the expressiveness. Now, let's take again a step back to where we started with the simple line inter-regression, where you have a loss function. You take the gradient with respect to the two parameters to fit a line. Here is again the same. So if you want to do a simple regression, you need to come up with a cost function and you fit the parameters. Say here again, that would be my model F with a lot of weights, thousands, hundred thousands, millions of parameters. Here you have the observation. And now how do you... sorry. I'm focused. So if you want to do regression, say you have certain, to come back to the housing idea, say you have like income and wealth, and you want to take out the maximum loan you could get. So the bank would have data on all the customers. They would fit the neural net. They would write down a cost function, J, and then they would, once they fitted the parameters, they would give you your loan conditional on your input characteristics. So that would be one classical cost function for simple regression problems would be a mean square error. If you have classification, this you have probably all seen is cross entropy. It's a measure essentially how close the empirical distribution that you want to fit with the model gets. That's a typical cost function for classification. Now, how do we do that in practice, right? So we want to find the arc mean of the cost function, so the gradient with respect to all these parameters. And now, you may all have heard in econometrics about some, minimization methods. In neural nets, we use a thing called stochastic gradient descent. So what are the building blocks for that? So say we have a neural net with just two parameters. Then the landscape of my loss function would look like this. So I initialize my neural net randomly with weights somehow. Then I start my optimization procedure somewhere, say here. Then I compute the gradient. I take the step. Then I compute the gradient again. I walk down. So this is the typical, intuition about gradient descent. So notice a few things. So first of all, this doesn't lead you automatically to global optimum. Despite the fact there is, optimizers that claim to be, globally optimum, none of them are. So like what we do here is a local optimization. So if you start your optimization procedure here, you may end up in a different minimum. This may also lead to, different, resulting predictions. So you just should be aware of that. When you fit the neural net within your threshold, that doesn't mean, you're at the true minimum. So, you need to do some robustness checks, but that's sometimes for another time to discuss. But the basic logic is loss function, you do your minimization, you end up somewhere in the local minimum, then you claim victory, and you do your predictions. So how does gradient descent, to remind you, technically work? So you have your neural net, and this neural net is a baby, right? So it hasn't seen any data. So it's just like, I have a 1-year-old at home, so I am speaking out of experience. So like it's born, it knows nothing about the world. So weights are initialized somehow. Now what you would do is, in classical, ways, you would compute the gradient with respect to all the components. This is fine for a linear regression, but like if you have a lot of data and a lot of coefficients, this part here would kill you. I'm just saying you need to compute the gradient. Then you would update the weights with this, like you have essentially all the weights. You do steepest descent. So here is the gradient, and here is eta, that will be the learning rate. It's just a parameter, but this can be adapted. So all parameters go downhill with a certain step size with the direction here. Again, this is a killer. Okay, so what can you do alternatively? You could say, okay, I don't want to do this enormous sum. Let me just randomly pick a single point. So like we had the picture before. So you just compute here at the single point, compute the gradient. But of course, this thing would be noisy. It would lead you probably anywhere. So what you do in neural nets, this is, well, batch gradient descent, it's called. So if you say you have 100 points, instead of estimating your gradient based on all the 100 points, you would randomly select 10. Based on those 10 points, you compute or estimate your gradient, you take a step, and you repeat that game. So that would be stochastic gradient descent or batch gradient descent. So again, for lack of time, I put you some literature up there, but it's an unbiased estimate of the true gradient. But mechanically, what you would do, you take a subset of all the points, and based on those, you estimate the gradient.
Sorry.
Yes?
So before you mentioned, and maybe I misunderstood this, but you said we use neural networks because we're somehow breaking the curse of dimensionality.
Yes.
So is this trick of using a fixed set of points, is that part of it?
Empirically, yes.
Okay.
Yes.
No, that's slightly different. So the base of the theorem of breaking the course of dimensionality is that you're approximating an arbitrary function right on the part of the spectral density that you need. So the way you want to think about it, the simplest thing is to think about a value. So a value like this, it basically says a solid putting frequency, solid putting mass in one particular frequency of the spectral density. Now think about the spectral density of, an extremely highly dimensional space that basically tells you it doesn't matter how big the dimension is, we are just putting the frequency what we need. And the reason you do mini patches or stochastic gradient descent is only for efficiency. So even if it takes 0.001 second to evaluate the gradient, you may need to do a gradient. So PALM, the most recent large language model of metaverse, has 1 trillion parameters. So if you will need to evaluate a gradient with 1 trillion entries, even if it takes 0.00001 second, times 1 trillion is out of seconds. So what you do is you select a little bit and you make this more efficiently, but that's not really at the core of the theory.
Yeah, so I mean, that's what I meant with empirical is exactly right. So I can point you to literature. So there's, as I said, with sparse grids, conditional on the architecture, it can bound from above convergence rate. But in practice,
in practice, it's super important. So the Simon is 100% right. I just want to clarify what the theorem of the breaking of the course of dimensionality is about. It's all about putting mass in the right frequency in the spectral density.
Yes.
So batch gradient system, do you change the batch after each step?
So I'm not fully sure if I understand it correct. So, but assume, say you have 10 points. Yeah, so like you do your estimate based on 10 points, you get the gradient, you update the weights, then you take another part of the points.
You're changing which batch, you're changing which set of points you use with each step.
Yeah, I need to speed up a little bit here. But so once you use all the data, so all the batches, this is called an epoch. Just if you go to the literature, it's that's called epoch. Now let me, again, like way too much material, but so let me just now quickly, as I said, there's a lot of self-consistent tools that you will find online. Now let me just take a 2 or 3 minutes break, not break, but intermezzo is the word called. So you have access to this cloud that I mentioned before. So now let me just quickly go there. So I provide you three notebooks, and so just that you see once what this looks like. This I need to change the screen. Share screen. So when you log into this thing, you see something like that. You have all the. I mean, it's hooked up to the kitchen repository. The important part is twofold. Like first of all, you have all the copies of the lectures. But here, if you go to the left-hand side, we pre-configured you a bunch of applications, right? So I prepared here Tensorflow for dynamic structural estimation. There's TensorBoard. TensorBoard is a tool from Google to debug. I prepared your MATLAB, and then there is like a Jupyter Lab prepared from Rafael from Swiss Supercomputing Center. So in order to, so like I was kind of not cheap, but I configured that for you. So you all have like four virtual cores with 16 gigabytes of memory. If you want to run any of those codes we will cover in the lecture, you need to launch first now it will take a little time because it launches an instance on Amazon Web Service or Azure. So like you press on one of those apps on the site. Yeah, this may take now a little while. But then the point is, yeah, let me run it there. You will have, it's a Jupyter Hub environment. So on the left-hand side, you will have like the navigator where you can click through, and then you will find, for instance, the notebooks that I provide you for today. So notebook 1, well, now I will have to wait. I will probably do it in the break. You would just need to click on notebook E01 gradient descent. This is a tutorial, essentially what we just discussed, like moving from gradient descent to stochastic gradient descent with simulated data and empirical data. It's the frequency of chirps with temperature. So you will have there a notebook. So anyway, I let it launch and check it. So it's all there. You should run that in your little spare time that you have remaining here and ask questions. So this is mechanics. Sorry, I need to change screen again. Okay, so now go. If you have questions, ask me in the break, or ask Alexandra or Pauline. They work with that tool. Now, I need to, in the last few minutes, I need to give a bit more context. So, to come back to the neural network terminology, we need to compute all these gradients, right? And how do we get there? So we need to compute the gradient of the loss function with respect to the various parameters. So here would be that the loss function. Now we want to understand, so how for instance, how much does it change if the weight W2 affect the final loss? And this is nothing else than the application of the chain rule. So if you want to know the gradient of the loss function with respect to W2, with a simple diagram, that would be partial derivative of the loss with respect to y hat times y hat partial W2. That's called backpropagation. If you were to be interested how sensitive the losses in a small change with respect to W1, so that would be here, you would apply again like dW to dW. Well, from the back to DC type. Well, dy over the delta 2, then DC1 over DC1. And you clearly see this is again like a massive application of dot product, like linear algebra. It's again like one of the reasons why GPUs or like all these special purpose hardware help you to compute this gradient. It's called backpropagation. Now, remember before, of course, I showed you the simple surface, where you can find the optimum. Like in reality, when you look into the literature, so this is one paper, you can look at it, they visualize some of the loss functions. They really look terrible, huh? So it's like to get down here and not get stuck in a local optimum. This can be. I'm not supposed to curse here in public, but like, it's a bad state of the world, so to speak. Now, of course, people. This is not our job. It depends, but like I think not. There's a variety of ways, to still have a fair chance to find to a relatively good optimum. And how do you do that? You could, for instance, so far, you could play around with the learning rate. So that means essentially in regions of the loss function surface, if you're confident to walk downhill, you could take big steps. If you're less confident to take small steps. So you would have an adaptive learning rate. So I'm not going into this one, but there's a lot of research going on. This just is a subset of the literature. The de facto way of updating the weights, or like, what is the learning algorithm people use in neural nets? It's probably Adam, well, you see, I don't have time for this, but there's a lot of research going on. Don't quote that up, but you may want to play around with different optimizers for the reasons said. Then, like, last few words also, like weight initialization. So I mentioned before, you randomly initialize weights from some distribution. Sometimes this can be critical depending on your model. You may end up with an infeasible state of the world where you want to train your network in. So there's also research going on subject to the architecture you choose. Like, if you have like ReLU activation functions, etc. Like people wrote codes, for what is the optimal way to initialize your neural net. So you should pay attention to this one. Then one thing what I mentioned before, a typical thing you face, if you have activation functions like this sigmoid or so, and you have a very deep neural net, you can face the problem of which is called vanishing gradients. So if you're far out from zero essentially, and you would stack a lot of sigmoids, if you think of the sigmoid as this S, and when you far to the right, it's very flat. You have a lot of those, and you multiply a lot of flat things, you have something which is close to zero. Now, there's a bunch of technical things. So most of the neural nets, you work in single precision. Historically, the GPUs had very little memory. Now they have a bit more. But also now data sets become bigger. So like you want to be efficient on the way you store the data. But now if you have single precision, and you have to represent numbers which are close to zero, you can get numerical nonsense. This is a typical thing with vanishing gradients. So if you have a lot of hidden layers, you need to be careful what sort of activation functions you choose. So like ReLU, they have good properties. They have also some bad properties. So they have discontinuity in they have a kink, so they don't have continuous gradients. And there's a bunch of other activation functions which can handle this the issue of vanishing gradients, one of which is a Swiss activation function. So you see here, they have the same properties in the limit as ReLU, but here like they're continuous in the derivative. There is CeLU and others, so you need to experiment with those things too. Yes, so I'll skip the geometric interpretation. So few more words and then I'll shut up. Now, we have this backpropagation algorithm, so we want to fit the parameters of the neural net. The question is, when do you want to stop? And like I'm just talking here empirically. So what you would typically do. So you want to essentially use a bunch of. Let me go here. You would want to use a bunch of the data to fit your model to, and a bunch of the data to validate your model. So like if you use different network architectures, so like you use say 70% of the data to fit your coefficients, then 20% of the data that you leave untouched, you use to say you have a network that has like 2 hidden layers, another one has 5 hidden layers. So then you evaluate on the remaining 20%, which is the optimal, the best model you would choose. And then on the remaining 10%, you would essentially do the out of sample testing. So this is sort of the splitting of the data you would typically do in empirical data. Now, what do I mean with notes on overfitting? Now the question is, when would you stop, right? Because so here you would have like, say if you have like a not very rich model in the classical way of polynomials, say linear lines, so this is underfitting. Your model has too little capacity. If you then would take a model polynomial, which is with a higher polynomial, you would have like an overfitting within the data. So you want to find some middle ground. Now in the context of neural nets, how would you get there? Say you just have training and test data. So you fit your data, and you monitor how the loss goes down. And then there's typically a sweet spot here. And if you hit that sweet spot, so I give the training, as long as the training test data error goes down, you continue. And again, this is just true for empirical, exercises. When we come to models, it's a bit different, but we hear that tomorrow. So you would stop here, because then clearly what happens here, because a neural net can have, like, as Jesus said, like millions, billions, trillions of parameters. Like you have an enormous capacity to overfit, but you want to have out of sample performance in the end of the day. So like when the test data error goes up again, that's not what you want in the end of the day. So that's why you have this thing which is called early stopping. There's a bunch of other techniques to avoid overfitting. And let me just go here. One would be dropout. It's also a line in TensorFlow you can ask. So in every iteration, you essentially, the algorithm would drop a bunch of neurons. This would essentially, you make sure you don't have too much dependence on single weights of a neural net. So one or two notes, and then I really need to stop. This early stopping, this is what you observe typically. But now recently, also actually in finance, this is interesting, there was a phenomenon, and I think also Jesus had that in one of his papers, this double descending, you had that, yeah. Right? So like, typically you would go down here, and then at some point you would stop. But like if you let a very rich specified model continue to train, like the out of sample error again goes down. This is an empirical observation. Theoretically, it's still very poorly understood, but on Saturday, Samuel Malamud will give us a bit more context of that. But I'm just saying, if you do empirical work, it may be, also simulation, but like in particular, if the empirical work and you have relatively large data sets and rich neural networks, then maybe if you have money, it may be worth to run a little longer to get better performance. Yes, and with that, like I put you up few notebooks. Now let me see if the talk started. Sure. Yes, so it started here. So you will have, like on my lecture in subfolder codes, as I said, you have a gradient descent notebook. You have those of you who have never worked with the Jupyter Hub. So this looks like like this. So you do a launcher. You have here different. Also here you would have like notebooks, Python, but you can also, if you have MATLAB launched, you have MATLAB. Then on the side you see here these notebooks. You can click on them, and then you can essentially just by Shift Enter, you can step through that. So this second notebook gives you a comprehensive introduction to what I just discussed. So it will generate you artificial training two-dimensional training data of an analytical function. Then we will set up, fully connected neural net. Then we will train it, see out of sample error. And then we will have a classification example where we have like a data set of 10 different types of clothes. And then this would take another 2 hours. So like you have here these codes, play with them. Play with them, get acquainted. And as I said, so this is one of the good news. So you don't need to marry to TensorFlow charts or PyTorch. It starts to be APIs to all of them. Yes. Sorry for taking a bit too much time. I hope you will have a lot of fun. From now on, there will be more economics, I promise. Yes, I take questions in the break, and then John will give in 10 minutes his actual introduction to the summer school. Remember, for him, it's now 4 4:20 in the morning, so it's real dedication to still step in.
The other hand is in Puerto Rico.
Hmm?
The other hand is in Puerto Rico.
Ah, yeah.
Maybe 5.
Gracias.